Good afternoon, everybody. How you guys all doing?
Oh, thank you.
Cool. I
Good.
just posted your lab that we're going to do today. Can you guys see it on Canvas now that I just updated like a minute ago?
I see it.
Cool. Okay, cool. Measurement and uncertainty. Exactly. That's the one. All right. So we're going to pick up right where we left off. Let me pull up my notes here. Hold on, let me put a little note here. One sec. Okay, I just had to do a little note to myself because like I just came from another class that went a little longer. Usually it ends 15 minutes before, but you know it was their first day of class. They had to ask lots of questions. So basically, it's the same class as you at SMC, just they don't have labs. So, and it's all in one day. They do 3 hours back to back. So let's go ahead and pull it up here. We left off here, talking about vectors in linear motion. Any questions about velocity and vectors? How's the homework coming along? Have you guys started it yet?
Yeah.
Great. Awesome. All right, that's where it goes. Glad to hear it. So, let's get back to where we were talking about acceleration. So we can change the velocity of something by changing its speed, but or changing its direction, or changing both its speed and direction. How quickly and in what direction the velocity changes is called the acceleration. So it's the change in velocity or the change in interval. So I'm going to use this capital D for delta here. This means change in. We're going to use lots of different Greek symbols. You know what kind of made me depressed? Is that they've already, you know how there's the delta variant right now? They've already got, so after they run out of Greek letters, going through the whole Greek alphabet, alpha, beta, gamma, delta, blah, 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 they also already got lambda is already a variant. When they run out of Greek letters, they're going to start using constellations for new variants after that. That made me sad. They've already got a plan for that, running out of Greek letters. I don't know. Does that make you guys sad? Makes me sad. But, yeah, they gotta have a plan for that. So, let's say you have a car that started from rest. Or let's say a car started at let's say we have a car that starts at rest and it starts at, let's say not rest, let's say at 30. Let me zoom in a little bit, it's a little tiny for that. Starts at 30 kilometers per hour and accelerate in 1 second. You have the accelerator on. It accelerates to 35 kilometers per hour. And then the next it is 40 kilometers per hour. And so on. What is the acceleration? The car. So it doesn't matter where we start and where we end up. What matters is the change between them. So we're going to have the acceleration. Sometimes it's abbreviated as A equals, draw a line right here. Boop, 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 boop. And we're going to make, it's going to be change in velocity, which I'm going to just abbreviate as V. This is the starting velocity right here. Let's say velocity to the right. And we're just going to keep on going to the right. Let's assume no change in direction for now. We'll talk about that later. So we have change in time underneath here. So we're going to abbreviate this as delta V divided by delta. By the way, if you want to know how you do this on a computer, it's going to be on a Mac, it's Option J to get this Greek delta symbol. I don't know how to do it on Windows. Does someone know how to do the Greek delta symbol on Windows? Because I do not know. Okay, so it's going to be the change in V was 35 minus 30 kilometers per hour minus 30 kilometers per hour divided by 1 second. Okay. So that's going to equal 5 kilometers per hour divided by 1 second. Now you can see that this is like weird units, so we got to convert hours to seconds to have this be in the same units. The book doesn't change it. I don't like how they don't change it. I'm going to change it. So we're going to multiply this by 1 hour equals 3,600 or 60 times 60. 60 times 60 seconds. Because 60 minutes in an hour. I'll do the whole thing. 1 hour is 60 minutes. And then, whoops. Is and then we have 1 minute is 60 seconds. And then also, let's move this down a little bit. So we're going to move, actually we're going to copy this whole thing like this. Yes.
Is this the same like conversion factors like that we use in like a chemistry class?
Yeah, yeah. Brandon's like, wait, hold on a second. This is familiar. This is like chemistry and unit conversion. Yes, yes, it is. You're exactly right, Brandon.
I have another question then.
Yeah.
Well, I mean I haven't had a chemistry class in a while, but how did you get rid of the seconds if you multiply by the hour? Wouldn't it be you wouldn't have to get rid of the seconds and then convert it into minutes, then from minutes to.
So I'm not getting rid of the seconds, getting rid of the hours, actually. I'm canceling this out, actually. So what I'm actually doing here is I'm canceling this one thinner. So this right here is going to cancel out this right here, and then this is going to cancel out that. Is going to cancel that. Actually, let me do it like this instead. Like this. So this is going to cancel out this. And then this is going to cancel out this. Does this make sense, Brandon?
Yeah, in my head, I don't know why I thought like in order for them to cancel, they'll have to be like let's say for saying like denominator against numerator and stuff like that. Like,
yeah, you thought I was canceling out the seconds. No,
yeah.
I'm not.
Yeah.
I'm going to actually get it from being in kilometers per hour to meters per second here, actually. So then the last thing I'm going to have is that 1 kilometer per hour, 1 kilometer is going to be 1,000 meters. Okay, and when I do this all together, whoops, I have it upside down. There we go. I was like, well, hold on. There, that's the right place. So this kilometer is going to cancel out that kilometer. So okay, I want you to move it. Okay, there we go. Canceling this out. And let's make it a different color, though. Let's make this like a green. And then we're going to cancel out this one here. That. Opacity, 50%. Okay. And so I get that having 1,000 divided by 360 and then times 5, I get a final answer of A equals 1.389, or just 8, right? 339 meters per second squared. Where the book just leaves it as 5 kilometers per hour second. I don't like that kind of weird combo of units, so that's why I converted it. And I'll let you know what the unit conversions are. Because it's not a chemistry or a physics class, a rigorous. Well, it's not a chemistry class, and this is not like the goal of me to test you more concepts. So I'm not gonna. While I walked you through how to do the unit conversion, I'll just tell you multiply by this factor to convert from kilometer per hour to meters per second. Sound good?
Yes.
Cool. So here are some questions from your textbook here. So what's the acceleration of a race car that whizzes past you at a constant velocity of 400 kilometers per hour? What do you guys think? Ooh. Zero. Why, Addy?
Because it doesn't indicate a change and it's moving at a constant.
Exactly. So it's 0. All right. Second question. Which undergoes a greater acceleration? An airplane that goes from 1,000 kilometers per hour to 1,005 kilometers per hour in 10 seconds, or a skateboard that goes from 0 to 5 kilometers per hour in 1 second?
The skateboard,
Why?
because it took a shorter amount of time to increase by 5 kilometers
Per hour.
per hour. Yeah.
Yes, exactly right, Timothy. All right, let's put that in. That's exactly right. Hold on, guys. Any questions about this? As the book says, velocity and acceleration are very different things. Distinguishing between them is very important. So, if acceleration, the change in velocity or change in time. Let me just do a new slide here. Where is it? Here it is. So, new. So, if acceleration is change in velocity over change in time, then velocity acquired is just going to be acceleration times time, assuming constant acceleration, which we will for most cases. So if you've been accelerating at 1 meter per second squared, or let's say 2. Let's say if a equals 2 meters per second squared, and it starts at rest, which is velocity of 0, and a ball starts at rest. Let's say a car starts. Oh, did you guys lose? Can you guys see it now? I just see that we probably lost connection there for a second. Do you guys see it?
Yeah, looks good.
Cool. All right. I just got a little. Participants can see your screen now. Like, uh-oh. There maybe was a time where you couldn't see it. Yeah. Oh, I forgot to say. I forgot to do the pre-lecture quiz today. Just too many things. People were trying to add to the courses, and it was a mad shuffle in the first week. So we'll start lecture quizzes next week, starting with chapter 4. So hopefully you'll read up for chapter 4 for Monday.
How early will those be released?
I'm going to try and have them ready by, at the latest, Sunday afternoon. But hopefully I'm going to have it done by tomorrow. Yeah, sorry, just lots of moving parts this week. Oh yeah, we don't have class on Monday. So yeah, we'll see each other again on Wednesday. Keep on forgetting I got a day off on Monday. Well, it's not going to be really off for me. I'm still be working. But in theory, I'd have it off. Okay, so after the first starts from rest, which just means velocity starts at 0 meters per second. After 1 second, the velocity is 1 meter per second. At the second one, second. I'll just say at t equals 2 seconds. At t equals 2 seconds, I'll say this will be t equals 1 second. I'm basically starting the stopwatch at, beginning. T equals 2 seconds. Velocity. Oh, nope. It's supposed to be after 1 second, it'll be 2 meters per second. Sorry. I said the acceleration's 2. After 2 seconds, the velocity will be 4 meters per second. Semicolons here. Semicolon, comma, and then semicolon at 3 seconds. Velocity will equal 6, and so on. So you can rewrite this in symbols as velocity equals your acceleration times time. Let me do it like this. Acceleration times time. Sometimes it's not even written with that. Like this, just AT plus what velocity you start at. Where this is v0 or v sub naught is what velocity you start at. Hold on. It's a little bit lower than that. There. Is the starting velocity. for constant acceleration. This is the general formula. It's in your notes. Then this and little sub notes. You should probably put this. Let me go ahead and box it. Put a little box here. I'm gonna put them in boxes sometimes, like this one here. This is probably a good thing to put on your formula sheet. Yes, Timothy.
Professor, why is the second square, like the A equals 2 meters per second squared?
It's a good question, Timothy.
Where does
Does anyone
the
happen to know
square
the
come
answer?
from?
Does anyone happen to know? It's a very good question. Why is it per second squared? So first, let's go ahead and figure out what is velocity in the first place. So what's velocity?
Speed?
Yeah. But going back to it, let's go back a couple things. It's going to be a distant, it's going to be, well, actually didn't really write it out. So let me go ahead and put it explicitly here. So I'm glad you asked, Timothy. Go ahead, Addie.
Oh, a vector quantity of instantaneous speed and direction.
Mm-hmm. Right. So it's going to be equal to, let me go ahead and steal what I had from here. Where is it? So just like how acceleration is this right here. Whoops.
So acceleration is the change with the variable change within constant velocity, while velocity is any given quantitative point in time.
Yeah. So no. Well, hold on. It's I didn't quite hear what you said. Hold on. Let me just finish doing this right here. So velocity is going to be change in let's call this x, or displacement, over change in time. So where x is displacement. So you see how like this has units of meters divided by seconds gives you velocity. And then you divide by velocity by t, you get acceleration. That's why it's per squared. And what were you saying, Addie? I didn't quite catch what you said.
Oh, it's all right. Thanks.
No, what did you say though? Could you repeat what you said?
Oh, that acceleration is the variables of change within the constant or the define the term again.
Well, sometimes acceleration is constant, sometimes it's not. But it's basically the acceleration is the change in velocity, and velocity is change in displacement. Or it's kind of like distance, but vector form. So displacement is the vector form of distance, where displacement is how far you're at from the origin at any given moment. Far you are from the origin at any given moment. Okay, so acceleration is just how velocity changes. It could also be how the direction changes too. So sometimes it is constant, Addy, and everyone else. Sometimes it is constant, and then you get this equation. Sometimes it's not, though. And they have to be more complicated. But everything in this class will be constant acceleration at most. If it's not, you'd feel like jerk. You know, if you ever had an acceleration in a car, you felt like you jerk forward or jerk back into it in a car. That's why it's called jerk. That would be the change in acceleration.
Okay, thank you.
Yeah, so you can keep on going. You can keep on going. What's the change in a jerk? And what's the change in the thing you call change in jerk? And so on. I think someone was clever and called it snap, crackle, pop after jerk, by the way. That's not standard, by the way. It's just someone being clever. But jerk is pretty accepted for change in acceleration. We're not going to talk about it too much, though. But it's pretty visual, like jerking forward in a car. Does that answer your question, Timothy? About like how it's velocities of distance over a time, or more accurately, displacement over time. And then you have the change in displacement over a change in time. That's why it's time squared.
Yeah. Okay, got it. Thank you.
Because we divide by time twice. If you took some calculus, you'd know this is the second derivative. But don't worry about that. If you're like, wait, what? Calculus? No. That's okay. Don't worry about
It's
that.
okay. I believe you.
Believe me. Yeah. It's a fancy way of saying, let's say we have a graph. Basically, all a derivative is let's say we have a fancy graph. How steep is this graph right here? That's all that is. That's what calculus is, or that's one half of calculus. The other half is like, what's the area under that curve? And I just summed up all of calculus. No need to take it anymore. That's all you have for calculus, right? Kidding. There's a whole bunch. But that's the ideas, though. So what this is like the slope, what we're doing here, technically. And instantaneous velocity is the instantaneous slope, what it is at a certain point. So if you had this curve right here, what's the slope right here versus the slope between 2 points? Anyway, this would be if you were doing like the 6 series or the 8 series or the 20 series. We would talk about those things. But here we're going to be conceptual. Sure, the equations, but don't worry about too much where they come from. Good questions, everybody, though. I really do like your curiosity. So, let's talk about Galileo and his slopes again. So the reason why he did inclined planes is it allows him to basically dilute gravity and be able to measure the acceleration of a small slope and then extrapolate over to when it's just falling straight down. So, let me just type in Galileo used inclined planes to dilute the acceleration due to gravity. And from a ball rolling down a very small slope incline is going to accelerate slower than one at a steeper incline. up until you're dropping it straight down. So, hold on. Let me just... It'll be easier if I can draw on here. Give me one sec. Just need to have my iPad here ready to go. Come on. Do, 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 do. Okay, can you still... Let me resume share. Can you see that again?
E1.
Cool. All right. So let me zoom in on it. So if I do, whoops, a little bit thinner. If I do dot, make it smaller right here. So if this is the angle theta here, these are all angle theta here. And this would be theta equals 90 degrees. So the acceleration down the incline, oops, is going to equal the acceleration due to gravity times sine of theta. So when sine theta equals 90 degrees, it's going to be 1. So it's going to be just g. And by the way, by using this measurement, he found that this method, he found that g equals 9.8 meters per second squared, or about 32 feet per second squared. Of course, he wasn't using the meter or the foot yet. Neither were really invented yet. So, but he did measure that. You actually can look at Galileo's notes. They're available. You can look them up. I don't have access to these ones, but I do know he has like his measurement of the Galilean moons. That's pretty interesting. Well, I'll show you guys when we come to that topic. But what was really weird is it didn't matter how big the object was. Very interesting.
So this measurement is fixed for gravity. The measurement for that gravity equals 9.8 meters per second squared is fixed.
Well, let's just say it doesn't depend on what size the object is, ignoring air resistance.
Okay. It depends on other. Oh, okay. Oh, okay.
So I'm gonna put a pin in that little asterisk that I was kind of with what I was kind of alluding right there. But yeah, there are some effects how the acceleration to gravity on Earth changes. One effect probably you might be able to think of is that it's different at sea level versus being at in Denver and high up. Altitude affects it. Being further from the center of the Earth will mean that the acceleration will be smaller. The mass of the object didn't matter as long as air resistance wasn't a factor. This is probably another reason why he didn't really do the drop off of the Leaning Tower of Pisa. One, it'd be really hard to time, and two, air resistance would be a factor on that scale.
So our book just openly lied to us?
Well, I wouldn't call it a lie. It's a story.
Okay.
It's a fun story, but probably not. I'm putting a little sorry. I'm putting a little cold water on the book's fun story. But I think, showing you guys heard that story. I'll also tell you the stories about the time that when Archimedes supposedly ran through the streets of Syracuse yelling "Eureka" naked when he figured out buoyancy. I repeat that because it's kind of fun to tell, even though that probably didn't happen either. But let's go ahead and show you what I mean by difference of air resistance. Watch these two things. Let me go ahead and stop the share so you can look at it more carefully. So, watch this pen and this paper. If I drop them, the paper takes a longer time to do it. But if I crumple the paper up and repeat the experiment, now they fall at almost the same rate, because I removed most of the air resistance as a factor. But if we got on the longer scales, air resistance would become a factor, more prominent factor. Okay. So in the book, I actually also approximate this as about 10 meters per second rather than 9.8. Makes the numbers easier. And for the purposes of this, do you guys see it, by the way?
Yes.
Cool. Where is it? Okay. So let's go ahead and consider dropping a rock off the edge of a cliff. If we approximate that the so consider a rock dropped off of the edge of a cliff. So dropped means that velocity initial is going to equal 0 meters per second. And let's approximate g, which is usually we say it's equal to 9.8 meters per second squared. Let's approximate that as how do you approximately equal to? Where is the symbol? Nope. Hold on one sec. Let me find it. There we go. I don't know how to get it, but I got it there. Approximately equal to 10 meters per second squared. Okay, we're going to change this to that one. And okay. So if we have it the acceleration g approximately equal to 10. So it's going to start at 0, and then at 10 after 1 second, and then 20 after 2 seconds. What's going to be after 3 seconds?
30.
Yep, and then
40 and 50.
Yep, meters per second. And so we're assuming no air resistance right now. Because air resistance makes everything messier. Wait, where'd it go? What? Hold on 1 second. There we go. And air resistance is negligible. How do I spell negligible? I can't tell. My dyslexia makes me not trust myself at all. So, by the way, I did say I have dyslexia, so things are going to get flipped around a little bit. And no, that's not how you spell negligible. But I got close. It's able, not able. Yeah. So, yeah. So, I know things go wrong. Like spelling errors, I'm not going to hold you guys to. If you guys get the right idea and you flip, like basically get close to the right answer, you'll get most of the points on things. It's really about like whether I can follow your logic, because the process is important. All right. Any questions so far? Let's go ahead and say you throw the object up instead. Let's say we threw it up at a velocity of 2 meters per second, or 20 meters per second. So after every second, it's going to lose, or 30. Let's say you threw it straight up at 30 meters per second. After 1 second, it'll now be at 20, then 10, then 0. Then negative 10, negative 20, negative 30, and then negative 40. The next one would be negative 50, and so on, after 8 seconds. Okay, so this also, it doesn't matter if we start at 0 or we start at a velocity. Here it was downward, and so here direction matters. Here direction matters. This problem defined up as positive and down as negative. So the initial velocity, v0, is going to be 30 meters per second, and acceleration is going to be negative 10 meters per second squared. So the direction matters here. And so we can still use that velocity equals AT plus V0. Okay, and so we can do this and make this subscript right here, V sub 0. That, and this one's going to be squared here. Everyone following along so far? Because remember how I said velocity requires the direction to be in there. The minus sign here will take care of the direction. Since we're only in one dimension here, whether it's positive or negative is enough to characterize its direction. Since the ball or rock moves in a straight line the positive or negative sign is enough to characterize the vector. Sorry, my neighbor's got a little noisy. Is it too much with my microphone? I can close the outside. You guys, is that... neighbor's starting getting a little rowdy. Cool.
You're fine.
Cute. It is a very directional microphone, so I do like it a lot. So, just was checking in with y'all. It's just not as stuffy if I have the window open. But I can hear it. Okay, so that tells you the velocity here. But how can we figure out how far it's gone? Between here and here, it went from being at 30 seconds to 30 meters per second to 20 meters per second. And then from here to here, it went from 10 meters per second. So it can't have gone as far, right? And then from here to here, it went from 10 to 0, and then 0 to negative 10, and then negative 10 to negative 20. So by symmetry, this distance should be the same as this distance, and this distance should be the same as this one, and this one should be this one. But what are those distances? Well, it turns out it's going to be proportional to the acceleration times the square of time. Okay, in this case, that would mean that y here, it's actually 1/2 the square of time. Why that 1/2 is there is due to geometry. If you're curious why 1/2 is basically, remember how I said, going, like, basically calculus is all about finding slopes and areas? Well, I'll show you in a second, is 1/2, let's do a space, a times t squared. So let's make that like this. So we got 1 and 2. And we're going to put a line between them like this. Make it a little thicker though. Maybe not quite that big though. A little smaller. A lot smaller. Okay. And we're going to shrink this whole thing down. And then move you on up. Okay. So this is going to equal 5 meters per second squared times t squared. So that's 10 divided by 2. Okay. Oh, minus 10. Minus 5 here. So from here to here. Oh, plus the initial velocity here. I almost forgot that. Plus. This is assuming assuming v0 equals 0 meters per second. If not, you have to add it in as plus v0 t. Except it's supposed to be other way. Okay. So in this case in particular, it's going to be copy, paste, and this is going to be 30. 30 meters per second. And we're going to go ahead and get rid of all this. Come on. Okay. All right. So then this is the general formula here. For how far it's fallen. How far it's fallen. All right. One last thing is that velocity vectors, I think I mentioned this before, but let me be extra clear, is that it tells you both how fast and in what direction. And then this is going to wrap up chapter 3. And then we'll start, we'll take a 10-minute break and we'll start the lab. So let's say we have a plane flying due north at 80 kilometers per hour, and there's a 60 kilometer per hour crosswind. The net resultant velocity is going to be 100 kilometers per hour at this direction right here. This is because it's actually it's actually hidden in here. This is a 3, 4, 5 right triangle here. They've just multiplied it by 20. So, if all the stuff from motion is confusing to you, be patient. It took, thousands of years for us to understand this. So I'm distilling a lot of the stuff that we've done for a very long time. And then even the calculus stuff was like a long time after that. So it's taken a long time, so be patient with yourselves. Oh, one thing of vocabulary, though, is that free fall means that you fall under the influence of gravity only, ignoring air resistance. So free fall means that you fall under the influence of gravity only. Okay. Any questions before I take a 10-minute break, and then we're going to do our lab. So you guys, if you aren't here right now, I noticed some people trickled out. You're going to have to do this on your own later, but I'm going to try and go over it as clearly as possible. All right, and we're going to just be randomized into groups of 3. Okay, see you guys at 3:13. Okay, so now that we've finished up chapters 1 through 3, I just want to check to make sure if you guys have any questions on those before we get started on the lab. Okay, have you guys started the homework yet, by the way? Because it's due Monday. Okay, so the lab actually that I posted, let me go ahead and send you a link here again, actually has a bit more than we're going to go over in this class. So I'm going to let you know that we're not going to cover propagation of uncertainty here. So let's go ahead and share this. Come on. Come on. Ah, go away. So let me share this. So we're not going to do this kind of stuff, propagation of error and uncertainty, because this is a conceptual physics class. It's kind of beyond the scope of this course. So just ignore this part stuff right here, and we're just going to skip and do this part right here. We're going to do this simulator like this. First one we're going to do is this one. So what I want you guys to do is I want you guys to measure the size. We're going to fill out the table right here. First, you're going to figure out fill out this table right here about what's the uncertainty in all of these things. Like, least count means what's the smallest tick mark you can have. And we're going to go ahead and you're going to fill all this out like this. And you're going to fill out, so you're going to do everything except, let me annotate, don't do this part here or this part, well, this part here. Don't do the uncertainty. That makes sense, everybody? Don't do the uncertainty for all these calculated ones. It's a bit beyond what I have time to teach you guys. So after that, so do everything except for the delta ones. Okay, so we're not going to do, don't worry about this, or this, or this. And don't worry about this. So don't worry about this. Don't worry about that. Or this, or this, and don't worry about this, and don't worry about that, or this. Does that make sense, everybody? How we're not doing any uncertainties? The original ones, yes. So going up, let me clear that. So the original ones here, you can fill out. the uncertainties here. But just not in the later tables. So fill everything out in table 1 and table 2, and tables 3, 4, 5, 6, you just don't fill out the uncertainties. And you're just going to go ahead and make an Excel sheet where you're going to have them. And then you're going to copy that Excel sheet. Let me just go ahead and show you what the Excel sheet would look like. Like this. So let's say that, clear. So let's say for the first one, you measured the length being 1, and then the vernier part of the iron block being 6. You have this right here. Fill this out like this. Yeah, you can do that too, Addy. Yeah. Just the only thing on the tablet is that you got to make sure you also answer out these pre-lab questions too. Okay, so for the first one, we're doing this one here. So you just, let me refresh this. It's actually going to be, let me share it with you guys. So when you first open up the link, you have to use the link. Apparently, sometimes if you try and do the links, whoops. If you try and do the links here, these are the correct links, like this one right here, and this one right here, and this last one right here. Sometimes it'll trip up your security. So what you should do is you should use these ones here. These ones here also give you the same links. So it's the vernier caliper simulation, the micrometer simulation, and the density simulation. So first things first, the micrometer one, or vernier caliper one. Let's go ahead and have the iron block. You close this down like here. So see right here, this is called the main scale, and this is called the vernier scale here. So let me go ahead and actually, I forgot to add in one last thing into your notes. Did this one? Yeah. Let me go ahead and share this with you, and then I'll put this in here. Share. New share. This one here. I'll put this also into your notes as well. Yeah. Go away. So, this is called the main scale in blue right here. And see how the inner jaw right here is how you clamp down on things? And this outer ones would push into things. It would measure inner distances. If this was like, you know, if we're going to be in the pandemic still in next spring, what if I teach this class again, what I'm going to do is going to have people buy little lab kits, like little $40 lab kits. And they're going to be able to play with them themselves rather than having to be simulations. So how do we read this? Well, if this is like a simple like ruler, you could only get like, you know, tenths of a millimeter or centimeter here. But with vernier calipers, you can use this vernier scale to actually get even more accurate. So step 1, you measure off the main scale as like 2.12, and then the first one on the vernier scale here, that tells you where you stop on the main scale. By the way, the vernier scale starts at 0, going up through 10. And that's how you get 2.2 centimeters. Get the next digit by figuring out, okay, which one of these tick marks lines up best with one of the main scales. And so that's going to be 2.8, like that. So this link right here, let me put it in the chat, gives the explanation of how to read it. And you can also play around with it right here. Okay. Questions on vernier calipers. I'll also put this in the lab as well. And then the other one, how does micrometers work? Let me just copy this and put this in as well. By the way, this is actually vernier micrometers. Yours are not vernier, but I'll show you how they work with vernier. So you have the barrel scale and the thimble scale. So the barrel scale rotates here. So this would be like 0, 1, 2, 3, 4, 5, 6, and these are half ones. And this is the thimble scale. And so this one actually goes one further and actually does tenths between them. So this would be 6.5, and then you add in this much. So this was 35, and I guess between the next digit was 6 and 8, and so they did 6.857. Yours doesn't go that far. Yours only goes up to, put the lead shot in. You inch it down. It only goes up to here. By the way, for the vernier calipers, it actually allows you to check it. I was getting that the screw gauge or the micrometer gauge wasn't actually getting accuracy. It was like this wasn't working. I don't know why. Let me refresh. But put it onto this one here. Because you can actually change what the screw gauge least count is. Put it to this one here. All right. Any questions about the micrometer? Or the vernier calipers? So what would this reading be?
centimeters. 12 millimeters, I mean.
12 millimeters, yeah. So this one lines up the best right here, the 0. So I'd say it's 12 exact, or 1.2 centimeters, or 12 millimeters exactly. And I'd say the 0 lines up the best right here. If I do the breadth here, this one, what would you guys say this one is?
25.7 or 25.1.
Yeah, I'd say. Yeah, I'd say 7 or. No, because you have to start here, Timothy.
Yeah.
All right.
Yeah, so it's.
So 2.6, 2.7.
That's 5 here. The longest ones here are 5.
So 2.5.5, I think, or 0.6.
I'd say 6.
Okay.
This one does work, by the way. So it's 2.56. The micrometer one doesn't work. So this one doesn't work because this one's supposed to be 1, 2, 3, 4. So it should be 4 millimeters. Point 81, 2. Wait, hold on. These are halves. Let's see. 1, 2, 3, 4, 5. Let's do 82. Yeah, it doesn't do it correctly. I don't know why. So don't worry about this checker. It doesn't seem to work. Then on to the density. So let's refresh this. So here you're going to measure the size of like the bob right here. You measure the grams. Don't worry about the newtons right now. Measure the grams. And then you're going to put it into volume here. Get the reading of the volume here in milliliters. Note the tick marks here. So this is going to be every This is 40. So this is 20, 25, 30, 35, 40, 45, 50. So it's not super accurate here for the volume. And then you put the bob in. And then you now have a new reading. Here, hold on. I can do this. Is that easier to read? Okay. And then you actually have it, check it right here. By the way, 1 cubic centimeter or 1 cc is 1 milliliter. So when it says grams per cc, that should work too. Okay, so going back to this right here, where to go? So in your Excel sheet, you're going to fill out this table entirely. You're going to fill out this table entirely. You're going to fill out this table. And you're going to fill out this one except for this. Don't fill out this part. And you're not going to include this part here. By the way, this is lowercase delta rather than the up. So the triangle is uppercase delta. This little squiggle is lowercase delta. Don't worry about the uncertainties because we don't have time to go into it. So just don't include this, or this, or this, or this, or this. And don't have to worry about this right here. Or this. And that should be it. Any questions before you guys get started on your lab? Should be pretty quick.